Today we're going to begin Chapter 4 on exponential functions. So we'll be looking at Section 4.1 as an introduction to exponential functions today. Okay, the question always comes up, why do we study different things? Exponential functions actually have a lot of practical applications to the real world. Here's some examples. Modeling population growth in a given area, modeling the spread of diseases and viruses. We're actually living right in the middle of this, modeling the growth of this COVID-19. Doing carbon dating of artifacts, helping coroners determine time of death, investments and interest are determined using exponential functions, and also loans are determined using exponential functions. So there's quite a few different applications of exponential functions. I want to take a minute and look at some graphs of the representing the COVID growth. Okay, so this one is representing North Carolina, and I'm not so concerned about looking at it from that perspective as this perspective here, which is the cumulative cases of COVID growth in North Carolina. And you can see that this is actually going to have the shape of an exponential function. You'll become much more familiar with that shape as we go on throughout this course, but basically with an exponential function, it's going to start growing fairly slow and then it takes off and goes much quicker. And when they keep talking about flattening the curve, the flattening the curve is where we want to get this to quit accelerating and actually become where it's not exponential in growth and kind of flatten out. So we haven't really done that. What we've done in North Carolina is go from what looks like an exponential growth here to a little bit more of a linear type growth with that. And so it's really important to kind of understand the type growth that we're experiencing with that. I wanted to look at some states that actually had some interesting shape to their graph as well. California is one. If you look at this, started out very slowly, then started growing exponentially and just exploding. And thankfully, it is kind of starting to level off a little bit and starting to have that curve flattened, so to speak, with that. New York, we know, fared pretty rough as with the COVID crisis in the beginning. If we look at that one, you can kind of see how this relates in terms of a graph. So you can see here is that explosion that they have. So it's definitely exponential during this part, and then thankfully it did level off. So it's not really exponential growth here, but we did have exponential growth here when it started. So the flatter we can get this, the more we flatten the curve, the better off we are in terms of this pandemic. But you definitely see how if this had continued on a truly exponential trajectory, we would be in it would be in serious problem for us today. Not that we're not dealing with a lot of issues, but it would be much worse than it is if it had continued to be exponential instead of actually flattening and leveling off. So at this point, this is kind of where the intervention started and started making a change as far as the number of cases and so forth. So thankfully, it did not continue to grow exponentially due to some of these interventions. Okay, so an exponential function is going to have a form like this, where we have some base. So here, if you have f of x equals 2 to the x, an exponential function, your variable is in the exponent. So we've seen things before like x squared plus 2x plus 3, which are polynomials, but with the polynomial, your variable is in the base, okay? But an exponential function, your variable is in the exponent. So we have to look at something called logarithms, which we will see a little bit later in this chapter, in order to even be able to solve for these exponents here. Okay, so I want to hop over to Desmos and kind of orient you to exponential functions and how they work. Okay, so you see that we have this basic form of a times b to the x. So with that, what we see is that we're going to start here with a equals 1 and b equals 1. So when a and b are 1, we basically have this straight line through the point 0, 1. So as I move the a, I want you to see what the effect of the a is on this. You can see that by changing the a, which is the number out in front of this, we're actually changing our y-intercept, okay? And when I change the b, let me move this back to where we can see it. Okay. So when a is 1 and then I'm going to move the b. You can see that as the b gets larger above 1, then it's going to grow more rapidly. Okay, so that exponential function just takes off the larger the b is. So you can see that the smaller the b is, the closer to 1, the flatter it gets. And then when it goes below 1, we actually see that it's what's called a decay function. So instead of growing, it actually starts at a value and decays. And that's what we see sometimes with radioactive decay and carbon dating and so forth, is the decay function. That's an exponential function. So it all depends on what the b is. A b that's greater than 1 is going to be growth, and a b that's between 0 and 1 is going to indicate decay. Okay, so this kind of summarizes what we saw in the Desmos activity. If a is greater than 1, then it's going to be a growth function. And if the, and then should be an a. If a is between 0 and 1, then the function is a decay function. If you have a negative in front of it, then that's going to be our reflection in the x-axis. Okay, so you can see here, these that are going down all have a base that's between 0 and 1, and then all these that are growing all have a base that's greater than 1. They're all passing through the point 0, 1 because they all have a 1 in front of that. So whatever is in front of that base is going to be considered your y-intercept. Okay, so here's a few I'd like for you to take a minute and write down whether it is a growth or decay and determine the y-intercept. Okay, the first one would be decay because the base is 1/3 and it would have a y-intercept of 6. This one would be a growth equation because it has a base that's greater than 1 and it has a y-intercept of 3. This one would be decay because its base is between 0 and 1. It would have a y-intercept of 1. This one would be growth because it is greater than 1, and it would have a y-intercept of 3. So some basic characteristics of our exponential function. First of all, the domain of an exponential function is all real numbers, so negative infinity to positive infinity. We can do translations, and that's really not going to affect the domain. If we look at the range is going to be from 0 to infinity because we have a horizontal asymptote here at y equals 0. Okay, so what happens is if we do any kind of shifting, any kinds of translations, the horizontal asymptote is going to go with it if it moves vertically. So that will affect the range if you're moving it vertically. If you move it horizontally, it's not going to affect anything with the domain and the range, but if you move it vertically, it is going to affect that. Okay, so here are a couple exponential functions. The first one has a base of 2, a base of 3, and a base of 10. Just kind of orienting you to that. As far as evaluating them, you just plug into the exponent itself. So f of 5 is going to be 3 to the 5th power. And here, if I have f of negative 2/3, then that's going to be 3 to the negative 2/3, okay, which is 1 over 3 to the 2/3, or 1 over the cube root of 9, depending on how you want to represent that. Okay, just for comparison, we've talked about quadratics before, and now we're talking about exponential. So I wanted to kind of compare these two and show you, when you start out at 0, it actually is that the exponential function's a little bit bigger. And then when we go up to 1, it's still a little bit bigger. At 2, the quadratic is actually equal to the exponential. And then for a short while in here, the quadratic is actually bigger than the exponential. But then after this point here, where they're the same again, you can see that the exponential function is going to grow much quicker than the quadratic does. And if you look down here, when x is 30, the quadratic is only at 900, but the exponential is at 1 billion. So in looking at, this is looking from 0 to 3, you can see here that the exponential is actually larger over the majority of that point. And then here you see that the quadratic kind of overtakes the exponential for just a short while, But then when we look at the big picture, it's clear that the exponential is going to outgrow the quadratic and be the larger value there. And that's why it's so alarming when we have some kind of bacteria or virus that's growing exponentially, is that it grows so rapidly because of that. Okay, so one thing you'll be asked to do with exponential functions is to take a graph like this and be able to find the base that represents that growth. So you're going to start with this equation, f of x equals a to the x, and we're going to use the point that's given. So here we're given this point. So this is my x, and this is my f of x. So in the place of f of x, I'm going to substitute 25, and in the place of x, I'm going to substitute 2. So a squared is 25, so a is going to be, take the square root of both sides, a is going to be 5. So my exponential function is going to be f of x equals 5 to the x, and that's going to be my equation. Okay, here's another one. This is our x and our f of x. So I'm going to replace this, and I'm going to put 1/8 equals a to the third. Okay, so 1/8 equals a to the third. To get rid of a cube, I need to take the cube root. So I'm going to have a equals, the cube root of 1 is 1, and the cube root of 8 is 2. So my equation is f of x equals 1/2 to the x. And that makes sense because this is actually a decay equation that's shown. And so we have a base that's between 0 and 1. Okay, translations of exponential functions. So over here, I want to look at some translations and kind of see how this plays into it. So if I look at this one and I translate it, because the C is going to be my vertical translation, that's going to move it up or down. If I make C, let's say, be +1, then what you can see is that this whole thing shifted up by 1 unit. So I originally had a horizontal asymptote at 0, but now my horizontal asymptote is actually going to shift up here to 1, and you can kind of see across there. If I were to move my C and let it go down to -1, then what you'll see is you'll see that the graph would have a horizontal asymptote at -1. Okay, so when I'm shifting it vertically, that asymptote actually goes with the graph itself and is going to help me to identify the domain and the range. So on these two shifts that I just demonstrated, the domain stayed the same. The domain stayed from -infinity to +infinity, but the range is going to depend on where that asymptote is. So like for instance, this one, when I shifted it down 1, the asymptote was at -1. So my range would now be from -1 to infinity. And because this is a horizontal asymptote, it actually doesn't touch that line. And so because it doesn't touch that line, it's going to be a parenthesis on that instead of a bracket. Okay, I'm going to actually go in here and put an equation. Okay, so this is what a horizontal shift would look like that's going to shift it to the right. And you can see what that graph looks like here. It got shifted to the right. So with this, what happens is the domain is going to stay the same. So the domain will still be -infinity to +infinity. And my range is actually going to stay the same as well. It's going to be from 0 to infinity with that. If I look at another one, if I've got y equals 2 times x plus 1, okay? So what that does is that's going to shift it, to the right. To the left because it's a +1. So I'm going to take this red graph and I'm going to shift it back to the left. And again, it doesn't affect the domain with that, and it's actually not going to affect the range. So horizontal movements are not going to affect domain or range. Vertical movements will affect the range, but not the domain. Okay, take a minute to identify the domain and the range and the asymptote on these, and then check your answers. Okay, these are the answers that you should have gotten. The first one would have been just a basic exponential shifted up 1. So the domain would stay the same and the range along with the asymptote would all shift up 1. Because remember the range for just the basic exponential function is from 0 to infinity and the asymptote is at 0. So all that gets shifted up 1. For the domain on the next one, it's again all real numbers. This one is a reflection in the x-axis. So instead of a graph that looks like this, it's actually going to be looking like this, reflected in the x-axis. So therefore, the domain would be negative infinity to positive infinity. The range is going to be negative infinity to 0. We're going to have that horizontal asymptote here at 0. For the next one, we're going to take this same graph here and then we're going to shift it up 1 unit. So it's going to look something like this. It's a little bit hard to kind of draw that in. So it's going to have a horizontal asymptote at 1 and its range is going to be from negative infinity to positive 1. And then the last one here, this would be a shift to the right 1 unit. So the domain is going to stay the same. The range is also going to stay the same, and the asymptote is also going to stay the same as just the basic graph itself. Okay, so we talked about one of the applications of exponential functions is compound interest. So compound interest is calculated using this formula here. So A of t is the amount that you have after a given time. P is your principal, or the amount that you start with. R is the rate. It does need to be as a decimal, so not as a percent. Give it as a decimal. N is the number of times it's compounded per year. And what that means is depending on how many times it's compounded, the interest is deposited, and then you can earn interest on the interest. And then you can earn interest on the interest on the interest, and so forth. So it's compounded a certain number of times per year. Sometimes that only happens one time if it's simple interest. But if it's compounded like semi-annually, then that would be 2. N would be 2. It would be compounded twice a year. If it's quarterly, then it's compounded 4 times a year. If it's monthly, it's compounded 12 times a year. Daily would be 365 times a year, and so forth. So T is the number of years that something is that you're earning the interest. Okay. So here we have an example. A sum of $1,000 is invested at an interest rate of 12% per year. Find the amounts in the account after 3 years if interest is compounded annually, semi-annually, quarterly, monthly, and daily. Okay, so this is my principal. This is the amount that we're going to be putting in the formula. This is my rate, but I want to convert that to a decimal. So it's going to be 0.12. And then 3 is my time. And then these are going to indicate the N. So annually, N would be 1. Semi-annually, N is going to be 2. Quarterly, N is going to be 4. Monthly, N would be 12. And daily, N is going to be 365. Okay, so this is kind of showing for each of these how you would set this up. When you go to put this in your calculator, I would actually put a second set of parentheses around these just to make sure that you're entering it correctly and getting the right answer out. So definitely try putting one of these in and make sure that you can get the answer that's given here. If you're having trouble with that, then you might just want to join me on a during office hours and let me make sure that you're putting it in correctly. Okay, here's one for you to practice with. Okay, so for this one, we're going to use our formula for compounding. Okay, so we're going to put 10,000 in, so that is my principal. My rate is 3%, so I'll put in 0.03. My N is compounded semi-annually, so N is going to be 2, and it's going to be raised to the 2 times 5, and that also needs to be grouped together. So if I put this in my calculator, I'm going to get $11,605.41. So if they put the interest in twice a year and let that interest earn interest, then I'm going to get $11,605.41 after 5 years. Okay, another aspect of this is finding what's called the annual percentage yield. So you may see this reported at times. So the APY is basically saying if it is compounded a certain number of times per year, what is the simple interest rate that is equivalent to that? So one way to think of that about that is if you look at this part of the formula, it's equal to 1 plus your simple interest rate. Or another way to think of calculating your APY is to do 1 plus your rate divided by n, the n raised to the nth, and then subtract 1 from it. So basically what you're doing is leaving off the principal because the principal is not really significant in this calculation, and we're considering it for time 1 year. So here our t would just be 1. Otherwise, it's basically the same formula you had worked with, except just take away the 1 at the end with that. So here, find the annual percent yield for an investment that earns interest at a rate of 6% per year compounded daily. So we've got for our APY, we've got 1 plus R over N to the nth minus 1. So we'll do 1 plus 0.06 over compounded daily would be 365 raised to the 365 minus 1. So this is going to be 1.061831311. We're going to subtract 1 from that, and that's going to give me 0.061831311. And we're going to round that to, usually it's going to be like 6.18%. Usually it's going to be reported to 2 decimal places. So we're going to move it 2 decimal places to convert it to a percent. Okay, here's one for you to practice with. Okay, if you plug that in, compounded quarterly, we're going to use 4. So we get this as our decimal, and this would be our percent. Okay, another example of exponential functions we talked about would be growth of bacteria and viruses. So here a bacteria culture contains 1,500 bacteria initially and doubles every hour. Find a function n that models the number of bacteria after t hours. So basically when we have an exponential function, it's going to look like this. And you might not use A and B in exactly the same, like those exact letters, but essentially it's this format here. This is going to be your initial quantity, how much you start with. And this is going to be your multiplier. Okay, so if it's doubling or tripling or whatever. So for this one, if we're going to come up with our model, we initially start with 1,500 and it doubles every hour. So we're going to do 2 to the x. And in this case, it's telling us to model it with an n. So we're going to do n of x equals 1,500 times 2 to the x. Okay, and then the last part, find the number of bacteria after 24 hours. So that's going to, we're going to put in 24 into our model, and we're going to get 2.5165 times 10 to the 10th. Okay. So what you're going to see there is you're going to see 2.5165 with a little E10 to the side, and that's just the same thing as scientific notation for times 10 to the 10th. Okay, that takes us to the end of the section on exponentials, getting kind of initially oriented to it. So if you have any questions, reach out to me during office hours and I'll be glad to help. Thank you and have a good day.